So classified paper 6, question from alternative to practical uh, topic acid, alkali and salt. Question 6, a student investigated the reaction between two solutions of A and B. So two solutions A and B of potassium manganate 7 was there in solution C. So two different concentration of A and B and they're mixed with solution C. First, three experiments were done. A burette was filled with solution A of potassium manganate and initial burette reading was recorded. Then measuring cylinder was used to pour about 25 cm cube of a solution C into a conical flask. So first what we did, we filled the burette with solution A, which is potassium manganate 7. And so this was solution A. And we filled this, the conical flask was filled with a 25 cm cube of solution C. And then solution A was added into a conical flask until the mixture just turned pink. We look, when potassium manganate KMnO4 is there, this is purple or pink in color. When it is reacting, when it was reacting, it was not showing. Like when it was reacting, the color start to disappear. The moment all of the C is used up, then the potassium manganate, extra potassium manganate, which is added, will make the solution colored. So the idea here is that like KMnO4 or potassium manganate is pink in color. This one is pink in color. When we add to solution C, potassium manganate was reacting with C, so the potassium manganate color was not like we are not able to see that color. But once all of the C is used up, then there is no more C left. As a result, what will happen? The potassium manganate, when it enters this mixture, it will show a color now. It will show a pink color. So what we did, a solution A was added into a conical flask until the mixture turned pink. The final burette reading was recorded, and about 2 cm cube of a content in a conical flask was poured into a test tube in experiment used in experiment 3. So we took out very small proportion 2 cm cube from this, and we did experiment 3, which is there. The rest of the content in a conical flask was poured away, and the conical flask was rinsed with water. The first one used a burette reading, initial and a final burette reading. You can use the screen annotation, initial and the final burette readings. So it was 1.1, 16.1, and when you take a difference, it will be 15.0. Yeah, that's right. So first volume, which we use, we can write it here, we use 15.0 cm cube of A for the reaction. Then we did the experiment again, and this time experiment 2 is done. The content in the burette used in experiment was poured, and the burette was rinsed with water. Then the burette was rinsed with solution B. First, why we rinse the burette with water?
To remove impurities.
To remove any impurities.
Yeah, to remove any impurity or to remove A. Then why we rinse with B?
To remove water particles.
To remove
To
water.
remove water.
Yeah. So first one, when we rinse with water, we remove A. And then we rinse with B to remove water, any trace of water. So now the burette is filled with B, potassium manganate KMnO4. And the conical flask, in the conical flask, I think we took, yeah, same amount of C was used. So we use C, which is 25 cm cube of C. Then a burette, from a burette, B is added until an indicator show a color change. Use a burette reading. You can use a screen annotation. What is the burette reading? Initial and the final. So initial burette reading is 1.9. The final is 39. So the total is 30. So we use 30 cm cube for a complete reaction. Can you identify which solution of A or B is more concentrated? Is it A or B?
Solution A.
Solution A. Because solution for
Solution
because for the same volume to react with 25 cm cube of C, I need only 15 cm cube of A. But for a complete reaction, I need 30 cm cube of B. So it means solution A, as I need small quantity, so it has more particles in a unit space. That's why A is having a high concentration than B. So the next question was, which solution of potassium manganate is more concentrated, and explain your answer. So we will write which solution is more concentrated. We'll write A. And what is the reason why A is more concentrated? Because smaller volume of A is required to react completely with C. Then how many times more concentrated, like when we compare the
We
concentration,
will take volume ratio and reverse
Vol
it. It would be 2 times as concentrated.
yeah. So we take a volume ratio and the concentration ratio will be opposite, because like when we take a volume ratio for A, it was 15, and for B, it is 30. So volume ratio is 1:2. So concentration ratio is always opposite of volume ratio. Like if one we need more volume, it means that is less concentrated. The one which we need less volume, it is more concentrated. So if the volume ratio is 1:2, then the concentration ratio will be 2:1. Because the concentration and the volume are always inverse. If we have a small volume, we'll have a high concentration. So how many times is more? So A is like twice concentrated than B. Is it clear, this one? How we work out the concentration ratio?
Yes, sir. Clear.
Yes, sir.
Okay. The next part, we have to predict the volume of a solution B that would be used if experiment was repeated using 50 cm cube. Now we want to repeat like how much B is needed when we use 30 cm, 50 cm cube of C. So as you can see here in the experiment 2, when we were using 25 cm cube of C, this was experiment 2, this is experiment 1. So in experiment 2, when we use 25 cm cube of C, so 25 cm cube of C, how much B was needed for a complete reaction? 30. So if we have 50 cm cube of C, how much B is needed? X cross multiply. So what you will find? You will find we need 60 cm cube of a B, because the volume is double. So volume of C is double. That's why volume of B will also be double. Like we need it twice. But what is the drawback of using a 50 cm cube? Burette maximum can hold
Burette needs to
refill, because burette maximum can hold 50 cm cube. So suggest a practical problem using a 50 cm cube of solution C. If we use 50 cm cube of solution C, we need 60 cm cube of solution B. And for 60 cm cube of solution B, what we have to do? So 60 cm cube of B, we have to refill the burette, because burette can maximum hold 50. It cannot hold 60. So once we
can
remove
still
50,
use measuring cylinder then.
but measuring cylinder won't be accurate in terms of measurement, the volume. We can use measuring cylinder, but it won't be accurate. It will be fast, but won't be accurate. So the problem, the drawback here, whenever you need like more than 50 cm cube of solution, and you are using a burette, in that case, you have to refill the burette, because burette maximum can hold 50 cm cube. Then give one advantage and one disadvantage of using a measuring cylinder rather than a pipette for 50 cm cube. What is the advantage?
Can
Can
measure
hold
range.
100 cubic centimeter.
Can measure a range, but the pipette cannot measure a range.
The best thing is if you compare their advantages, the best advantage is like using a measuring cylinder, you can transfer the solution quickly, faster. So using a measuring cylinder, we can transfer the solution quickly.
But it is inaccurate.
And disadvantage, it is inaccurate. Then experiment 3. The experiment 3, results of experiment 3 are shown. When we, like, what is experiment 3? In experiment 1, we took out a small proportion of sample from the mixture and we add sodium hydroxide, a green precipitate form. What this give an idea?
We can have
It can
chromium
be
or
iron 3 or
iron 2.
chromium.
Iron 2.
Yeah, because iron 3 is red brown, so it can be iron 2 is giving a dirty green precipitate. So this give an idea there might be iron 2. Then aqueous sodium hydroxide was added to a reaction mixture, saved from experiment 1 a red brown precipitate. What gives an idea? It might be iron 3. This can be chromium, but the thing is, what might happen? What conclusion can you draw about solution C from this experiment?
It contains
It contain iron 2 and it contain iron 2, and that iron 2 might be oxidized from the surrounding due to the surrounding oxygen. That iron 2 might be oxidized to iron 3. You can mention chromium, but the thing is, if it was a chromium, it won't change, the precipitate won't change the color. Usually, like example, if it is green, you mentioned iron 2 or you mentioned chromium. But the thing is, as they mentioned, these precipitate which are formed, like initially the precipitate were, there were green, dirty green precipitate.
they are
And
basically saying it remains.
yeah, and these are the dirty green
Chromium will dissolve.
Yeah, partially soluble. The dirty green precipitate are there, and these dirty green precipitate, with the passage of the time, they turn into red brown. The same precipitate turn into red brown. So if dirty green turn into red brown, so it means it shows that there is a change in oxidation number for iron. Like originally it was iron 2 and then it become iron 3. So what conclusion we can draw about? We can say that there was iron 2 ion in the solution which was oxidized by air to iron 3. So iron 2 has turned into iron 3 or oxidized. Is this clear, the last part?
Yes, sir, clear.